representing a simplified atmosphere. After a while, they all accumulate on the same butterfly. A very nice object that we can admire endlessly. These are real problems for mathematicians and for scientists also. Instead of describing the future starting from a given initial position, which we know is impossible, we will instead try to describe the attractor. What does it look like? How do the internal dynamics work? In the 1970s, Berman, Guckenheimer, and Williams proposed a simple model for trying to understand the Lorenz attractor. Here is a strip of paper. Let's fold it, and cut it, and glue it together. And we have a special object in space. Let's go to the starting line. Here we go. We drive, and a little while later, we are back at the starting line. But we are at a different point of the starting line. From here, a new path starts. Our position on the starting line is given by a number x between 0 and 1. At 0, we are on the left, at 1/2 we are in the middle, and at 1 we are on the right. If we start from the point x, then we will return to the point 2x if x is smaller than 1/2. And we will return to the point 2x minus 1 if x is larger than 1/2. In other words, when the car moves, the points where it meets the starting line are doubled at every turn, except we need to subtract 1 if the result is greater than 1. It's a bit like the horseshoe. The dynamics in continuous time get replaced by dynamics in discrete time. Namely, by the successive places where we cross the starting line. Look, we start off from 1/3. We arrive at 2/3. And then we arrive at 4/3. But we must subtract 1, that is to say, we arrive at 1/3. So, we are back to our original starting point after 2 rounds. Thus, we have a periodic trajectory of period 2. Here is a trajectory of period 18. Periodic trajectory passes successively through the left and right ears following a certain sequence. Well, it can be shown that all sequences are possible. And of course, not all trajectories are periodic. Whatever the infinite sequence of lefts and rights, there is a trajectory that follows that destiny. What is the relationship between the Lorenz attractor and the model made of strips of paper? Well, it wasn't until 2001 that the mathematician Tucker showed that the paper model accurately describes the movement on the Lorenz attractor. For each trajectory in the Lorenz attractor, there is a trajectory in the paper model that behaves in exactly the same way. Is it possible that the movement of the atmosphere can be reduced to continually doubling a number x between 0 and 1 and subtracting 1 if the result is greater than 1? Of course not. All of this is much too simplistic, but it is an illustration of the phenomenon. Simple things Mathematicians love them. Why has the butterfly effect become so popular? Perhaps because it gives us back our freedom. The legacy of Newton's cold determinism sometimes leads to a kind of fatalism. The Lorenz butterfly claims that, small as we are, we can have an influence on the world. Good news for us.